Seth asked me to announce, which I think was a good idea. I organize a online student combinatorics seminar link. And first of all, here's the link. Here's the link to my slides for today. And maybe I'll get the link to the seminar at the end. But if you know of anyone that a graduate student in combinatorics that you think should give a talk, definitely let me know.
So our last talk today is given by Sarah Brauner from University of Minnesota. She's going to talk about, the title is on the slides. Okay, please.
Hi, yeah, thank you. Thank you for the opportunity to talk and for organizing the conference and for everyone coming to the very last talk of the day. I know there's been a lot, so I appreciate you being here. And today I'm going to talk about a type B analog of the Whitehouse representations. So the sort of big idea of this talk is that I want to take some property of the symmetric group that brings together topology, representation theory, and combinatorics and generalize it to type B. And so this is the type A story right here, this picture. And I don't expect you to understand right now what this picture is saying. So the goal of this talk is to explain what this picture means, and then tell you about my contribution to this story, which is to generalize this picture to type B. Okay, so what I'm going to do is I'm going to tell you about the symmetric group representations I'm interested in. They're called the Eulerian Representations. And then I'm going to interpret those representations topologically using configuration spaces. And then I'll do the whole thing over in type B. So I'll tell you about the type B representations and the topology in that context. Okay, and so I'm going to start with the Eulerian representations. And really this story starts with a combinatorial subalgebra of the group algebra of the symmetric group, which is called Solomon's descent algebra. So I'm going to try and keep things sort of very non-technical today, but what you can think about this algebra, if you've never seen it before, is it's some combinatorially defined subalgebra of the group algebra, and its basis is indexed by integer compositions of n. And here's the definition for experts, if you're familiar. Okay, and so this is a very famous algebra in combinatorics, and one sort of natural question is there a family of idempotents that decomposes this algebra? And Garcia and Reutenauer in 1989 produced such a family. I'm going to write them like E lambda, and they're indexed by partitions of n. And so these form a complete orthogonal primitive family of idempotents of this group, of this algebra. And I'm going to sort of omit the definition because really what I'm interested in is a coarser family of idempotents that I'm going to get by summing over some of these Garcia-Reutenauer idempotents. So in particular, these things are indexed by partitions. So what I want to do is I want to sum over partitions of a fixed length, okay? And I'm going to do that for k from 0 to n-1, and this is going to give me exactly n idempotents, okay? And here's what they look like in the case of S3. Okay, and so I'm going to be talking about representations of the symmetric group. So to make sure that we're all on the same page here, the irreducible representations of the symmetric group are indexed by partitions of n. And here, when I'm talking about an irreducible representation, I'll just write the partition itself. Okay. And then another thing that we're going to need is the branching rules of the symmetric group. So this is a way to restrict a representation from Sn to or Sn plus 1 to Sn. And what I'm going to do combinatorially is I'm just going to take my partition and I'll remove a box in all possible ways so that I still get a partition. So for example, here, here's my partition. This is a representation of S3. There are two boxes I could remove. I could remove this box, or I could remove this box. And so what I end up getting is this direct sum here. Okay. And so the reason I bring this up is because what I'm interested in with respect to these idempotents today is the representations that they generate. So for each idempotent, I'm going to think about the kth Eulerian representation, which I'm defining to be the representation generated by the ideal generated by each idempotent in the group algebra. So for example, if we look at this idempotent here, this is an unsigned sum of every permutation in S3, right? And so if I multiply by another permutation of S3, all that's going to happen is these terms will rearrange, but I'll get the same term in the end. And so another way of saying this is that actually the representation that that idempotent generates is the trivial representation. Okay, the other ones are a little bit harder to see, so I'll just tell you what they are. This one looks like this, and then this last one looks like this. And you might notice this is a decomposition of the regular representation of S3, which is going to be true in general. Okay, and so there's a lot of interesting properties of these representations. The one I want to highlight today is that they actually have this additional structure that even though I've defined them as representations of Sn, they can be realized as representations of Sn plus 1. So to formalize that, I'm going to say that a representation V of Sn has a lift to Sn plus 1 if I have some Sn plus 1 representation W that restricts to V. So the way that I think about this is W sort of has all of the information that V has, and then it has some additional information. And so a preview for what I'm going to say is that the Eulerian representations have a lift. And so I'm going to sort of skip over how this lift is defined, but I'm just going to tell you that this is a theorem of Sarah Whitehouse, who proved that every Eulerian representation can be lifted to Sn plus 1. And this is the representation that I'm going to write as this lift, and I'm going to call these the Whitehouse representations. So let's see what this sort of looks like in the case of S3. So here are the Eulerian representations that we have. And so I want to think about what representations of S4 will restrict down to these representations. So for example, this trivial representation here, the only thing it turns out that will work is this trivial representation of S4, because this is the only block I can remove. Okay, for k equals 1, the representation that I end up getting looks like this, right? Because I could remove this block, I get that partition. I can remove this block, I get that partition. Okay, and then the last one, the representation ends up being that irreducible, because I can remove only this block. And okay, so this example is a little bit misleading because it looks like everything's irreducible over here, which is not always going to be true. And it also looks like this lift is unique, which is also not always going to be true. So there's like, in general, you could lift a representation in multiple different ways. Okay, so to recap what I've said so far, we have this combinatorially defined algebra, and then we had a family of idempotents in that algebra that generated a family of representations of Sn, and those representations had this extra structure that they could be sort of realized in Sn plus 1. But so far from what I've said, I haven't really told you or given you any intuition for why this is true. And so what I want to do now is sort of explain topologically why this happens. So to do that, I'm going to think about configuration spaces. So a configuration space of R to the D, I'm just thinking of this as n points or n tuples. Each of these xi's lives in R to the D, and I just require that they be distinct. So for example, if D here is 1, this is exactly the complement of the Braid arrangement, because these planes are the coordinates where xi is equal to xj. Okay, and so in general, Sn is going to act by permuting coordinates. And so what I'm going to do is I'm going to take the cohomology of this space. And when I do that, that action is going to tell me that I get an Sn representation on this cohomology by functoriality. And this cohomology, it's been studied a lot in a lot of different contexts. It turns out it has, it's concentrated in degrees that are multiples of d minus 1. Okay, and I'm going to stick to the case that D is 3 for today. So the sort of remarkable connection between these configuration spaces and Eulerian representations is that for every k where this cohomology is non-zero, each graded piece of this cohomology ring is exactly described by an Eulerian representation. So here's what this looks like in S3. So this information we already knew. The sort of new information is that I'm actually describing pieces of a cohomology ring. Okay, so what about the Whitehouse representations, the left? I want to be able to topologically interpret them as well. To do that, I want to think about SU2, which is the group of 2 by 2 matrices that have determinant 1. And importantly, it's homeomorphic to the 3 sphere. So here I'm kind of thinking SU2, the intuition is it's coming from the fact that it's the 1-point compactification of R3, but it's also a group. So I need those two properties together. And I'm going to think about first the configuration space of SU2. And this n+1 here should tell you that this is a preview of the Whitehouse representations. So this is how I'm going to get my lift. Okay, so I'm thinking of this as n+1 points in SU2 that are distinct. But now, because this is a group, it acts diagonally on this whole space. And so what I'm going to do is I'm going to mod out by that action. And this is actually the space that I'm going to care about. And I think it's helpful to think about what is a typical point in this space. So let's say that n+1 is 4. A typical point just looks like this, but because I have a group and I've modded out by the diagonal action, I can multiply through by P4 inverse, and I get something that looks like this, right, where 1 is my last point. And the point is that I can always do this. So a typical representative of this point is going to be this n+1 tuple where qi is not equal to qj is not equal to 1, and then 1 in the last coordinate. What this looks like pictorially is, okay, I can't draw a 3-sphere, but let's just pretend that we're in the 2-sphere context for a second. This 1 is like the North Pole. And so what I'm saying is I'm allowed to pick n points on the sphere that are not equal to each other and not equal to the North Pole. Okay, and so the sort of idea, the reason that I want to be looking at this space is that there's 2 natural actions on it. The first is by Sn+1. So this is an n+1 tuple, right? So I can permute these coordinates. But then because I have this description of a typical representative of my space, there's a very natural Sn action where I just permute the first n coordinates. Okay, so to sort of formalize why this matters, I want to relate this quotient space to the configuration space that I know is related to the Eulerian representations. And to do that, I'm going to stereographically project. So again, the intuition here is I've picked n points on the sphere that are not the North Pole. I might as well have picked n points on my in Euclidean space. So the sort of same thing is true when I move from S3 to R3. And it turns out that this is a homeomorphism. When I stereographically project the first n coordinates and I forget this last coordinate. And so the sort of upshot here is this space captures the natural, or captures an Sn+1 action that sort of relates to this space. And so when I move to cohomology, what this is really saying is that this representation of the configuration space lifts to this representation of Sn+1. And the theorem by Early and Reiner is that this lift exactly describes the Whitehouse representation. So here we started with our Sn representations. This whole thing simultaneously lifts to a representation of Sn+1. So this theorem is really about this isomorphism here. Okay, and this now tells me my type A story. So I have my symmetric group representations here, my Sn representations here, and then my Sn+1 representations here. So I can think of them as being sort of coming from these idempotents in the descent algebra or as the cohomology of this configuration space, and then I can lift the whole thing. Okay, so now I want to sort of do the same thing for type B. And when I say type B, I'm thinking of this as the group of signed permutations. And so the first step is to give some analog of this this representation story. And so first I need to generalize this descent algebra, which was that algebra that had a basis indexed by integer compositions. And it turns out that the right generalization here is called the Mantaci-Reutenauer algebra, which I'm going to write like this. And again, it's some combinatorially defined subalgebra of the group algebra of Bn. And now its basis is going to be indexed by signed integer compositions instead of integer compositions. So you should think of this as these are integer compositions of n's, but now I can have my parts be positive or negative. So it's sort of very natural generalization, type B generalization. And again, we have idempotents that decompose this algebra, introduced by Monica Vazirani in her undergrad thesis. So I'm going to write these idempotents like G lambda, but now lambda is going to stand for a double partition. So that means two partitions whose size together sums to n. And again, I'm going to do this thing where I sum over these G lambdas, where I'm going to take lambda plus to be a fixed length. Okay, so I'm going to get some coarser idempotents, and in particular, I'm going to get n plus one of them. What you should think is that these G lambdas are generalizing those the Garcia-Reutenauer idempotents, and these GKs are generalizing my Eulerian idempotents. And again, we're going to get a representation by thinking about this ideal. And so the theorem is that, or the sort of preview of the theorem is that this representation has a lift to Bn plus one. And so to understand where that lift is coming from, we need to move to topology. Okay, and so now I want to find a type B analog to this logical story. And so when I'm thinking about type B, instead of thinking about configuration spaces, I'm now going to be thinking about orbit configuration spaces. And I think this is sort of just most clear in our example. So for us, we're going to have G to be Z2. And it's going to act on SU2, which again is S3. And the action is going to be the antipodal action. So pictorially, that's like sending the north pole to the south pole. Algebraically, it's sending P to negative P in SU2. Okay, and again, I'm going to think about the orbit configuration space of SU2, which is defined as, okay, I take n plus one points in SU2, and I require that Pi is not equal to plus or minus Pj. But again, because SU2 is this group, I can mod out by my diagonal action. And so now my representatives of the space are going to be like P1 through Pn, where I require, okay, Pi is not equal to plus or minus Pj is not equal to plus or minus 1. So now I'm picking points. I'm not allowed to pick the North Pole or the South Pole, and I'm picking endpoints on the sphere where if I pick this point, I can't pick its antipode as well. And again, we have this sort of situation where this space exhibits two actions. This action by Bn plus 1, where now I'm permuting and negating coordinates, and this action by Bn, where I'm permuting and negating the first n coordinates, okay? And so again, I want to sort of use this framework where I stereographically project to obtain a genuine orbit configuration space of R3, so not just a quotient orbit configuration space. And so I do that, and okay, I'm going to sort of sweep under the rug some technicalities here about the space that I get, but this is the type A homeomorphism that I had when I stereographically projected. In type B, I'm going to get a homeomorphism between this quotient space that has the Bn plus 1 action and a Z2 orbit configuration space that has like a slightly strange condition. But nonetheless, it actually ends up describing these representations that are coming from those idempotents in the Mantaci-Reutenauer algebra. So the theorem is that for every k where I have one of these representations, or equivalently where this cohomology is non-zero, I have an isomorphism of Bn representations. So that's saying that this cohomology is describing this representation, and that representation lifts to a Bn plus 1 representation, which is exactly described by the cohomology of this quotient orbit configuration space. Okay, and so here is sort of a summary of what happened. This is my type A story, where I started with idempotents in the descent algebra, and I realized them as pieces of this cohomology ring of the configuration space, and then that whole story lifted to Sn+1. And then again, we have the same thing happening here. So I started with idempotents in the Mantaci-Reutenauer algebra. I looked at their representations. It turns out that those representations are describing the cohomology of this orbit configuration space of R3. And then this whole story sort of lifts to Bn+1, where now these representations are describing the cohomology of this space. Okay, thank you.
Thank you.